In the last class, we discussed a lot about analysis of the proton NMR spectra. We started by simulating the spectrum in a hypothetical example of CH, CH2, CH3 coupled among themselves with the different coupling strengths. Using a family tree approach, we synthesize the stick plot of this spectrum for CH group, CH2 group and CH3 also. And we saw in a given molecule, depending upon which is the functional group you are looking at, the pattern can be entirely different. It could be doublet of triplets, quartets of doublets, varieties of things we saw that. And afterwards, we started really analyzing this molecules, spectra of molecules, including simulation of a molecule called CH2D2, where we simulated the spectrum for carbon 13, proton and deuterium. Both of them, all of them are coupled among themselves, carbon 13 in its natural abundance, and carbon 13 and proton are spin half nuclei, deuterium is spin 1 nuclei. We just saw when we simulated the spectrum how in a small molecule like this, depending upon the nuclei of your interest, the type of spectra we are going to get, the appearance of the spectrum can be entirely different. That is what we observed. Then we took a realistic example of a small molecule. Right from small molecule, we started analyzing proton spectra based on the chemical environment. Assuming we have some knowledge about shielding and de-shielding, we always started with the CH3 group which is coming at the very high field, and then looking at the splitting pattern when the CH3 is coupled to CH2, CH3 is coupled to another group like that, what is the possible splitting pattern, using that idea, and also using the intensity pattern, and with the idea of the chemical shifts, ranges of the chemical shift which appears because of shielding and de-shielding. We did the analysis of large number of molecules. Fairly from simple molecule we went to complex molecule. Not too complex, simple organic molecule, to some extent is complex. Molecule may not be big, but spectra are complex. Then I wanted to introduce to you how we can analyze the spectra of molecules containing phenyl groups. We took the example of a monosubstituted benzene where we saw orthoprotons. Orthoprotons will experience one ortho to the substituent, that will experience one ortho coupling and also one meta coupling. And as a consequence, I said it can be triplet or triplet of doublets. If you look at the metaprotons depending upon two ortho couplings are identical or not. If they are identical, again it is going to be triplet, otherwise it is going to be doublet of triplets. That is what we saw. And then we also went into the example of benzene, in which we took the example of molecule like asymmetrically ortho disubstituted benzenes, like this. We took the example of asymmetric ortho disubstituted benzenes, and I said if I look at the proton A, there is a possibility it can experience ortho coupling, meta coupling and para coupling, all are of different strengths. As a consequence, it is going to be doublet of doublet of doublet. It is going to give you 8-line pattern. That is what we saw. It is going to be like this. We get 8 lines. Whereas if you look at proton B, I said proton B, again it has two ortho couplings which are different. As a consequence, you may get 8-line pattern because it has two ortho coupling and meta coupling. Whereas if you go to, this is the splitting pattern you are going to get. One ortho is split into a doublet, other ortho will split each of these into doublet of doublet, then para will make it 8-line pattern. If you go to the, assuming a situation if the two ortho couplings are identical, not different, in which case you are going to get the triplet of doublets. Large triplet comes because of two ortho couplings are equal, and then each of the triplet then is split into a doublet because of another para coupling. This is how it is. It is a triplet of doublet. And of course, what happens to the HC and HB? There HC can be doublet of triplet if two ortho couplings are equal, because HC can experience two ortho coupling and one meta coupling. Similarly, HB experience two ortho coupling and one meta coupling. The pattern for both of them could be DDD, doublet of doublet, or if the two ortho couplings are equal, again you are going to get triplet of doublets. That is what we are going to get. Only thing is the appearance pattern will be different because of the coupling strengths are different. That is what it is. So we got the pattern similarly for of course HD, 8-line pattern we should get. With this, now we want to continue further today. We will look at asymmetrically meta disubstituted benzenes. What will happen if they are asymmetrically disubstituted like this, in which case all the protons are chemically inequivalent. HA, if I look at it, it experiences 2 metacouplings and one para coupling. Both the metacouplings can be different because the substituents are different, in which case you are going to get 8-line pattern for the proton HA. If accidentally metacouplings both are equal, as I said, it is going to be a triplet of doublets. These 2 metacouplings will split this into a triplet if they are equal, and then para coupling will make it triplet of doublets. What happened to proton HA is like this, it is going to be 8-line or like this. Okay, we go to the proton HB. How does proton HB comes? Very simple, you should see, look at it. Now this is we are looking at proton HB. This has one ortho coupling and 2 metacouplings. Obviously, ortho coupling is going to be a large doublet, and each of these doublet peak splits into doublet of doublet because of 2 metacouplings. If the metacouplings are equal, it is going to be large doublet and then it is going to be triplet. Okay, each of them would be triplet, otherwise it is going to be 8-line pattern. Exactly what similar thing happens if you look at proton HC. This experiences 2 ortho coupling and 1 metacoupling. I am sorry, 1 para coupling. Again, if the ortho couplings are accidentally equal, it is going to be a triplet, and then para coupling makes it doublet, triplet of doublets. So these are the things which you should know, how when a phenyl group is present in a molecule, depending upon what is the type of substitution, you can have different patterns. For example, if you look at HD, again it is all are chemically equivalent. HD is experiencing 1 ortho coupling and 2 metacouplings. Again, it has to be a large doublet because of ortho, and each line is going to be 4-line pattern depending upon if the 2 metacouplings are equal or not, otherwise it is going to be a doublet and it is going to be a doublet of triplets like this. That is the pattern you are going to get. So this is the idea, just I wanted to tell you, if you have a phenyl group present in your molecule, how you go ahead and analyze this thing. So we will go to the example of asymmetrically disubstituted benzene group, asymmetrically para disubstituted. Remember this para disubstitution, in which case if this in principle at a low frequency spectrometer, this is going to be strongly coupled spin system. I already explained to you what is strongly coupled. These 2 protons are chemically equivalent, but the coupling of this and this could be different. There can be coupling between A and A prime also. Similarly, these 2 B and B prime are chemically equivalent. There can be coupling between B and B prime, and also B prime to A coupling and this coupling all are different, they could be different. As a consequence, this forms a strongly coupled AA prime BB prime spin system, and generally AA prime BB prime spin system, if you analyze, you should get 24 peaks, well separated groups of 12 lines. But if all of them are resolved, if normally in big molecules, if generally if they are not resolved, you are going to get what is called 2 doublet like patterns. It is like 2 doublets in case of asymmetrically disubstituted para disubstituted benzenes. So with this idea, how a spectrum will come for a phenyl group, let us analyze the spectrum of this simple molecule. We have, see this molecule is a little bigger molecule. We have 7 chemically inequivalent protons, 4 of them are situated in this phenyl ring and 3 are situated in this phenyl ring. Where is the, if you start looking at it with the idea I already have given you, you have to look at the phenyl ring which experience ortho coupling, metacoupling, para coupling, etc. Start thinking. If you look at this in these 2 molecules, I would fairly say this proton 3 is easy to assign, because this experiences only metacoupling here, becomes a small doublet, and then if at all you resolve, there can be a para coupling. It could be doublet of a small doublet with a separation of 1.5 hertz, and each of that line could be a doublet. So if it is not resolved, long range coupling, fairly you can say this should be a doublet with a small separation. If you look at the spectrum, I would say this is the peak which is coming. So fairly I would say that could be proton 3. And then you look at the other thing. Then if you look at this one, this experience an ortho coupling and a metacoupling. This has to be a large doublet, and then a large doublet because of ortho coupling of 8 hertz, around 8 hertz, and then metacoupling of 1.5 hertz. It is going to be doublet, and each line of the doublet is split into a doublet. It is a doublet of doublet like that. Where can you think of that? Look at it, it is one possibility, could be here. We do not know. That could be one of the idea. That is how you have to start. If you look at this one, what is that you are going to look at? If you see here, If the para coupling is absent here, he said there is not visible, then only thing which it can experience is an ortho coupling. So it has to be a doublet. You find out where you are seeing the doublet here. Of course, this is a big doublet. I would say this could be proton 6. I would say this is proton 5. This is proton 3. This is my first case. We will see whether it is true or false. Okay, we can go ahead and then start interpreting everything slowly. Okay, now we will start looking at it. What I said is correct. It is a proton 3. It is a doublet of 2.4 Hertz coupling coming because of meta coupling. Then I said this is the sixth one. It has to be a doublet. That is also correct. My guess is correct. See, idea with which we discuss about how the pattern comes for different protons, how the splitting pattern is there in the phenyl group, I could make the assignment like this. Then of course what I said was true. This is a proton 5. This has to be doublet of doublet. Large doublet is because of this thing, and then ortho coupling, and then it is split into a meta coupling because of this. So it is a doublet of doublet. Similarly, you can extend this. Of course, if you go to this proton, this is ortho, meta, para, all the 4 are there. It should be 8-length pattern. It could be doublet of doublet of doublet. Very clearly you can see. One interesting thing you should know is when there is a heteroatom substituted in a phenyl ring, if there is a heteroatom, ortho couplings are generally very small, not 7 or 8 Hertz. As a consequence, here you see ortho coupling is only of the order 5 Hertz. So I would fairly say this is proton 3 prime. And then go extending further, if you go to this one, then for proton 5 prime, this is very interesting because it experiences 2 ortho coupling and 1 meta coupling. I told you if the ortho couplings are nearly same, then you get a triplet like pattern, and each line of the triplet is going to be split into a doublet because of meta coupling, and this is what it is. This is 5 prime. Similarly, next is 4 prime. Exactly, this experiences 2 ortho couplings and 1 meta coupling. This also should be like that. Okay. And now how do you distinguish between these two? Of course, one which is at close to the nitrogen, this ortho coupling is smaller and this ortho coupling is larger. Very easily you can find out. Okay. And then with that we understood ascend 4 prime also, 5 prime also. What is left now? 6 prime. 6 prime is very easy. It has to be ortho coupling 1 doublet and doublet of doublet because of this. If this para is not resolved, it is going to be 2 doublet of doublet like this, similar to what we saw for 5. Exactly that it is. So very easily you can make the assignment of the molecule containing the phenyl group with the idea I gave you about splitting pattern for ortho meta protons depending upon the substituent where it is situated, whether it is ortho, meta, symmetric, asymmetric substitution. You can start arriving at it. Okay. There is also a way we can predict the aromatic proton chemical shifts, especially if you know what is the substituent. This has been worked out over the years by many stalwarts in the area. Every information has been tabulated. If in a given molecule there is a particular substitution, how this will affect the chemical shift of the neighboring protons, that has been tabulated. That is called substitution effect. And for this is for phenyl group. Of course, we can also do for aliphatic group protons also. I am giving an example for a phenyl group. But in which case, if you want to calculate the or predict the chemical shift values of protons of the phenyl group, starting base value is proton chemical shift, which is to be taken as 7.28 ppm. That is the base chemical shift of protons. Using that, then you look into the additive effect of other substituents based on whether it is in the ortho position, the substituent with respect to the substituent, whether observing proton is in ortho, para, and meta position, and then what is its contribution. It is simply an additive factor. You can use that and then predict the chemical shift of all the protons of the phenyl group. It is fairly simple, and for that there is a table like this. Remember, this is easily available in any of the books. Let us say I look at the NO2 group. If I am looking for a proton, if it is if the substitution is ortho to that proton, then for the base value you have to add plus 0.91. If substitution is instead of ortho, it is the meta to the proton you are looking at is having a substitution at the meta position, you have to add 0.24. If the proton you are looking at has a substituent at para position, it is plus 0.37. Not only is addition, it can also subtract with negative signs. So for different functional groups, this has been worked out. By and large, it gives you precise values, by and large. I mean exact, of course nothing can beat the experiment. You cannot say it is an experimental value, but by and large it comes close to the experimental value. Using these values of the substituent, and then the values which has been given in the table, we can predict the chemical shift of all the protons. Now I will take an example like this. It is a para-dinitro-benzene. If I look at the this one nitro group, I look at this proton. This proton has one substitution in the para position, NO2, another NO2 is in the meta position. Go back to the table here. Okay. In this table you can find out the values. If it is in the ortho position, plus 9 you have to add for the base value. If it is in the meta position, 0.24 you have to add to the base value. Now come back here, it has got values in such a way, if you look at any of the proton, it always you can see one of them is in the ortho position, other in the meta position. So take the base value, for which add value of the substitution in the ortho position and value for the meta position, and this is the total value. So you can predict the value of the chemical shift of each of these protons, all are equivalent here in the para-dinitro-benzene, and you see this is the predicted value and this is the experimental value, fairly close, very close, fairly. And this is the way you can even predict the chemical shifts of many of the aromatic protons if you know what is the substitution. Let us take the example like this. Instead of para-dinitro, let us take meta-dinitro. Meta-dinitro-benzene if I take, remember here all the 4 protons are chemically inequivalent. Let us start with calculation of the, of course not all the 4, these 2 are same, and only there are 3 possible chemical shifts, 3 are chemically equivalent, these B are identical. Okay, and now I can calculate the chemical shift, predict it for all the 3 protons. Proton A, I will start with proton A. In the case of the proton A, take the base value 7.28, and for proton A we have NO2 substitution in the ortho position, there are 2. What did we say in the table? You go back to the table here, ortho position value is 0.91. So add it, 2 times you have to add, because there are 2 nitro groups in the ortho position. Then if you add it with the base value, this turns out to be 9.1 ppm, and look at what is experimentally observed, 9.073 ppm, very close to predicted value. Go to proton B now. Proton B, what will happen? If you any proton if you take, one is in the ortho position, other is in the para position. Ortho position is 7.28 and meta position, ortho position, this is the base value 7.28, ortho position is 0.91, and then of course para position is 0.37. That is the contribution for the chemical shift depending upon where it is. So for I will take this proton, or even if you take this proton, this is ortho and this is para, so it does not matter, you can take whatever it is. Finally if you add this thing, this is the value you are going to get, 8.56, and look at the experimental value 8.573. Same way for proton C. Proton C, what is happening is both of them are in the meta position. Base value you take 7.28, add the meta position value 2 of them, it turns out to be 7.76, and what is the experimental value? 7.805. Fantastic. Look at this one. This is the way if you have an idea of the substituent and looking, if you know which are the proton you are looking at in the phenyl group, it is possible for us to predict what are the aromatic proton chemical shifts. It is possible. Okay. We will go ahead, and most of the time you can use this idea to assign the peaks, starting with you can assign based on the multiplicity pattern and also based on the predicted chemical shift. I will take this one. This is a real molecule. We have to analyze the spectrum of this. This is a methyl metanitrobenzoate is molecule. I look at proton HA. Remember this has one NO2 group in the ortho position, one C double bond O OCH3 group in the another ortho position. So take the base value for 7.28, and NO2 I know it is already 0.91 in the previous example we took for the ortho position, and for this CO2 CH3 if you go to the table which I showed you, this is 0.74. So the contribution for proton A because of NO2 is 0.91 ppm, and because of CO2 CH3 is also 0.74 ppm. Add this to the base value of 7.28. Now, if you add all of them, this is what is the chemical shift for proton A. You can predict it. This is the proton chemical shift. Similarly, predict the chemical shift of proton B, C, D, okay, everything you can mark it. So, if this is A, this could be B, C, D. I can mark everything and then calculate everything. And for proton B, again you take which is ortho, which is in the meta position, all those things you can find out. So, B, this is ortho, and I am sorry, this is para position. If you take this one as B and you can know the value of it, you add it up, it turns out to be 8.53 ppm. Similarly, for proton C, proton D, values can be predicted like this. What are the experimental values? 8.68, 8.86, 365, 415 and 7.652. And this is the what you can look at it, each of them. HA is 8.93. See, this is very close to this one, 8.86, and of course HB is 8.53. 8.53 is somewhere here, or you can take this one, and 8.35 is here, and this is 7.4. Not precisely, but close by. But that is enough to assign, make the assignment, and then further you can iterate it, and then go down the precise, make it very precise, looking at the multiplicity pattern and etc. This is what it is. Now, the proton A, if I consider, this is proton A, based on my chemical shift. Proton A is the one which comes at the lowest field, 8.93. Based on that, I made a assignment. This is A, B, C and D. This is A and D, based on the predicted value. Let us see why my predicted value agrees with the splitting pattern or not. Okay. Use the idea of predicting the chemical shifts of phenyl protons using the table. Make the assignment. Now, let us see whether my assignment agrees with the predicted value or the splitting pattern that I already discussed. I told you how you should think of the splitting pattern for different protons of the phenyl group. Proton A, you take it. What are the possible splittings you can think of? This is one meta coupling, other meta coupling, and then a para coupling. This is how it is. There is one meta coupling. This is the chemical shift is always at the center, and each line of the doublet splits into each another doublet. It will become doublet of doublet because of meta coupling, and this is also there. This will split into para coupling. So, it will become 8-length pattern. Here these meta coupling and this meta coupling are not identical. As a consequence, it is not triplet of doublet. It is only doublet of doublet of doublet. So, it is 8-10 pattern. It agrees with the chemical shift predicted, also agrees with the splitting pattern. Go to proton B now. Proton B experiences one ortho coupling and then two meta couplings. I am sorry, two meta couplings it experiences. You look at this proton B, it experiences one ortho coupling and two meta couplings. So, this is how it is. Proton B one ortho coupling and one meta coupling is like this and other meta coupling is like this. So, it will become again doublet of doublet of doublet. Pattern is agreeing with our chemical shift predicted value. What is the next one? Proton C. Proton C is interestingly it experiences two ortho coupling. Okay. Proton C, look at this one. This proton C has one ortho coupling, another ortho coupling, and then one para coupling. The one ortho coupling splits into a doublet, and another ortho coupling splits each of these line into a doublet, and then para coupling splits each of them into doublet of doublet of doublet. So, we are going to get 8-10 pattern. Actually, in principle, it is a triplet because two lines are overlapped. Triplet of doublets you are going to get very easily. Actually, in principle, there is a resolution here. If you carefully see, it is not overlapped. So, it is 8-length pattern. Go to D. What pattern you expect for D? One ortho, one meta, and another meta. So, one ortho coupling is a large splitting, and two meta couplings are there, which are split like this. So, it is going to be 8-length pattern. Meta couplings are different. Fantastic. Now, we know how we can analyze spectrum for different protons of the phenyl group. Based on the substitution, we predicted the values and then used a multiplicity pattern and then analyzed it. Very easy. Okay, with this idea, I will take one more example, very simple example. This is aspirin as a tablet. It is also called acetyl salicylic acid. This is a structure given. See, there are COOCH3 and COOH. 2 ortho substituents are there in this molecule, and we have 4 protons. All are chemically inequivalent because the substituents are different. There is no symmetry operation here. There is no symmetry element. So, it is like that. Of course, plane of symmetry is there. Apart from that, there is no chemical equivalence. That is it. Now, we will predict the chemical shifts. Substituent effect on proton A. Start with proton A. Base value is 7.28, and it has got proton A, if you consider, 1 ortho position COOH and meta position C double bond OCH3. Use the value given in the table. I put it and add up everything. It turns out to be 8.13 ppm. Very good. Similarly, if you go to the proton B, what happens? This one is in the meta position, other in the para position. For the meta position it is 0.17, for para position it is minus 0.9. You have to add. It is not only always additive, it is also subtractive. It turns out to 7.36 ppm. Similarly, work out for proton C. Proton C, if you go, you will see proton C has 1 in the meta, 1 in the para, similar to B only. Exactly, you work it out. And then, of course, remember the substituents are different. So, values are different, it need not be same. Finally, for proton D, this is what the value you get, and these are the predicted values. All the predicted values for all the 4 protons based on this using the table we could do. Now, what are the experimental values? These are the experimental values. Look at it, 8.113, this is 8.13, 7.346, 7.36, 7.61, 7.63, 7. Fairly accurate. Very precisely we could do that. You see, we can predict the values of the proton chemical sheets. Now, go back and assign this one. With this idea, we know A comes to the chemical shift of A is the least shielded, more shielded, it comes to the downfield, then C, B and D. You have to assign as AC, BD. Okay. Why it is least shielded, everything is more of chemistry, you can understand. That is because of COOH substituent, it is electron withdrawing group. Okay. And for the case of D and B, there is a electron donating group is there. Fine. This is the spectrum. In the COOH group is there and OH group is also. OCH3 there, COOCH3 and OH is there. Of course, this is CH3 group and COOH group is here. Always I told you OH group will be very, very broad. When I was talking to you about selection rule and natural line width, I told you, what will happen? Because of the resident time of the proton in the excited state is very small, it relaxes very fast. So, OH and NH peaks are usually broad. That is what I said, you remember that. So, this is COOH, this is CH3, that is assigned. Then you have to assign only the remaining protons. Remaining 4 protons are mentioned here. What was our assumption based on the chemical shift? The proton, one of them which is shielding downfield is proton A, which is resonating at downfield is proton A, then proton B, C and D. That is what we predicted. Let us see whether it agrees with our splitting pattern, what we have already worked out. For proton A, there is an ortho coupling, one meta coupling and one para coupling. True, there is one ortho coupling and each line is split into doublet because of meta coupling, and if you carefully see, each of them is further split into doublet of doublets. So, it is the 8 line pattern. Fantastic, it agrees with our assumption. Go to proton C now. Proton C, it experiences 2 ortho coupling from here, one ortho coupling, another ortho coupling like this, and each line of them becomes a doublet because of coupling with proton meta coupling. Same with proton B. I am sorry, this is proton C. That is also of course same, 2 ortho and meta. Proton B is also like that, 2 ortho and 1 meta. Exactly similar pattern, except the resolution is not there. This also gives 8 lines. Okay. HB also experiences 2 ortho and 1 meta coupling. What about D? This is proton D. This experiences 1 ortho coupling, 1 meta coupling and 1 para coupling, all are different. So, what will happen? What is the pattern you are going to get? It is a large coupling, ortho coupling, each of them is split into a doublet meta coupling and each line is split into 2 lines like this. You get 8 lines here. There are 8 lines here. If you carefully see, each of them is a 2 line, doublet, 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 8 line pattern. So, it agrees, multiplicity pattern agrees, chemical shift what we predicted agrees. So, very easily you can make the assignment, and this is the aspirin tablet, phenyl. So, acetyl salicylic acid, we can make the assignment here very easily. So, that is how we can understand. Please remember, proton A has one ortho meta para coupling, proton C has ortho meta coupling, proton B has again ortho meta coupling, and proton D has ortho meta and para coupling. All the pattern very easily we could assign without any difficulty. So, now fairly you got the idea how we can analyze the spectrum of the molecule, simple molecule, with lot of examples we took yesterday about aliphatic group molecules, only aliphatic groups. I did not take the example of the phenyl group, and based on the multiplicity pattern we made the assignment of all the protons without any difficulty, based on the shielding and de-shielding, where it is resonating, and looking at the multiplicity pattern in the molecule, which is the group sitting next to it will tell me what is its multiplicity pattern, and I am able to analyze this. That is easy, but only in the case of the phenyl group we have to be little bit careful, because the phenyl group we have 3 different couplings, ortho meta and para, depending upon the substituent, whether it is symmetric or asymmetric, whether it is ortho meta or para disubstituted, depending on that we have different multiplicity pattern for different protons, that we understood how to do that. I told you how multiplicity pattern comes for different substitution, if it is a mono substituted, disubstituted, etc. That is a pattern we know, ortho meta para, whether it based on whether having a large couplings, whether 1 coupling, 2 coupling or 3 couplings. We can say one proton experiences 2 ortho coupling of identical strength, and then 1 meta coupling or para coupling, it will be triplet of doublets. Like this we could explain everything. Sometimes there could be complications and you may not be able to assign so easily. So, we can predict the values of the chemical shifts of the phenyl protons, because we have the table of values where different substituents what it can contribute for the protons depending upon whether it is ortho, para or meta position with respect to the substituent, and there are n number of substituents. Take a molecule, look at the proton position, look at it, and for that proton look at it what is the substituent in the ortho, meta or para position. Pick up that value from the table, take the benzene value of 7.28, that is the base value, and then keep adding all the other values, finally arrive at the values, that is predicted chemical shifts. By and large they agree with the experimental ones, and use that, and then use the knowledge of splitting pattern, fairly you can make the assignment for all the phenyl protons. This is how we can go ahead. Next we will go for other topic about heteronuclear coupling in the proton spectrum. So, I am going to stop here. Thank you very much.